Hello everyone, my name is Suman Chebalu. I'm a master's student in computer science at Wayne State University. This is my second semester and this is a video presentation about Mapreduce. Introduction to Mapreduce. What is Mapreduce? Mapreduce is a programming model for processing large data sets with a parallel distributed algorithm on a cluster. We can define Mapreduce as a computational approach that involves breaking large volumes of data into smaller batches and processing them separately. A Mapreduce program is composed of a map procedure that performs filtering and sorting, such as sorting students by first name into queues, one queue for each name, and a reduce procedure that performs a summary operation, such as counting the number of students in each queue, yielding name frequencies. So let us examine what the origins of Mapreduce are. In the early 2000s, some engineers at Google looked into the future and determined that while their current solutions for applications such as web crawling, query frequency, and so on were adequate for most existing requirements, they were inadequate for the complexity they anticipated as the web scaled to more and more users. These engineers determined that if work could be distributed across inexpensive computers and then connected on the network in the form of a cluster, they could solve the problem. But they found out that distribution alone was not a sufficient answer. This distribution of work must be performed in parallel for the following three reasons. The processing must be able to expand and contract automatically as workload increases or decreases. The processing must be able to proceed regardless of failures in the network or the individual systems. Developers leveraging this approach must be able to create services that are easy to leverage by other developers. Therefore, this approach must be independent of where the data and computations have executed. Thus, Mapreduce was born. Mapreduce was designed as a generic programming model. Some of the initial implementations provided all the key requirements of parallel execution, fault tolerance, load balancing, and data manipulation. The engineers in charge of the project named the initiative Mapreduce because it combines two capabilities from existing functional computer languages, the map function and the reduce function. So let us examine how Mapreduce works. The inputs of the map function are a set of key value pairs. When a Mapreduce job is submitted to the system, the map tasks, which are processes that are referred to as mappers, are started on the compute nodes, and each map task applies the map function to every key value pair that is allocated to it. Zero or more intermediate key value pairs, list K2 and V2, K2 being the key and V2 being the list of values, can be generated for the same input key value pair. The intermediate results are stored in the local file system and then sorted by the keys. After all the map tasks complete, the Mapreduce engine notifies the reduce tasks, which are also processes, to start their processing. The reducers will pull the output files from map tasks in parallel and merge sort these files to combine a file with key value pairs into a set of new key value pairs, K2 and list V2, where list V2 is a list of values, where all values with the same key K2 are grouped into a list and used as the input for the reduce function. The reduce function applies the user-defined processing to process the data. The results, normally a list of values, are written back to the storage system. As an example, given the table's user visits as shown in the table 2, one typical job is to calculate the total ad revenue for each source IP. A possible MapReduce specification of the MapReduce functions are shown in algorithms 1 and 2, which we'll see shortly. The algorithms assume that the input data set is in text format, where the tuples are separated by lines and the columns are separated by the character pipe. So as we can see, the algorithm for map function, each mapper parses the tuples assigned to it and generates a key value pair, source IP and ad revenue. The results are first cached in the mapper's local disk and then copied to the reducers. This is called shuffling. In the reduce phase, key value pairs are grouped in the form of source IP, ad revenue 1, ad revenue 2, ad revenue 3, and the list goes on, where the source IP is the key and the values that you see in the form of ad revenue are the values. So they are grouped based on the keys, that is source IP. So now that they're grouped, each reducer processes these pairs by summarizing the ad revenue for one source IP, and the result, source IP, sum of that ad revenue pertaining to the source IP is generated and returned. That was one example. Let's take a look at another example of MapReduce. Assume you have 5 files, and each file contains 2 columns, a key and a value in Hadoop terms, that represent a city and the corresponding temperature recorded in that city for the various measurement days. This is just an example, but you can imagine that the real-world application will be quite simple, as it's likely to contain millions or even billions of rows, and they might not be neatly formatted rows at all. In fact, no matter how big or small the amount of data you need to analyze, the key principles we're covering here remain the same. Either way, in this example, city is the key and temperature is the value. So we can see one file with these tuples, Toronto with a temperature of 20, Whitby at 25, and the list goes on. Out of all the data we have collected, we want to find the maximum temperature for each city across all the data files. One key thing to note here is that each file may have the same city represented multiple times. Using the MapReduce framework, we can break this down to 5 map tasks, where each mapper works on one of the 5 files. The mapper task goes through the data and returns the maximum temperature for each city. For example, the results produced from one mapper task for the data above will look like this. Toronto 20, Whitby 25, New York 22, Rome 33. This is the result from one file. It sorts these key value pairs according to the values, in which Toronto 20 is the highest for Toronto, Whitby 25 is highest for Whitby, so the list goes on. Let's assume the other 4 mapper tasks working on the other 4 files produce the following intermediate results. Toronto with a maximum temperature of 18, Whitby with temperature of 27. So these key value pairs are generated from each file, where these keys have the maximum temperature of Toronto has a maximum temperature of 18. Whitby is 27, New York 32, Rome 37. So they produce these key value pairs. These are the intermediate results. These are not the final results yet. All these final output streams will be fed into the reduce tasks, which combine the input results and output a single value for each city, producing final result. So among all the files, no matter how many occurrences of the key Toronto has come, the highest maximum temperature is 32. Same goes for Whitby. Whitby's highest temperature across all the files is 27, and so on and so forth. So let's take an analogy here. You can think of a map and reduce task as a way census was conducted in the Roman times, where the Census Bureau would dispatch its people to each city in the empire. Each census taker in each city would be tasked to count the number of people in that city and then return their results to the capital city. There, the results from each city would be reduced into a single count sum of all cities to define the overall population of the empire. This mapping of people to cities in parallel and combining the results, which is like reducing, is much more efficient than sending a single person to count every person in the empire in a serial fashion, which would be time-taking and not scalable. Let's examine some salient features of Mapreduce. Programmers implement their own map and reduce functions, while the system is responsible for scheduling and synchronizing the map and reduce tasks. Mapreduce is being used increasingly in applications such as data mining, data analytics, and the scientific computation. Its wide adoption and success lies in its distinguishing features, which are summarized as follows. Flexibility. Since the code for map and reduce functions are written by the user, there is considerable flexibility in specifying the exact processing that is required over the data rather than specifying it using SQL. Programmers can write simple map and reduce functions to process petabytes of data on thousands of machines without the knowledge of how to parallelize the processing of a MapReduce job. The underlying framework does the job for you. Scalability. A major challenge in many existing applications is to be able to scale to increasingly large data volumes. In particular, elastic scalability is desired, which requires the system to be able to scale its performance up and down dynamically as computation requirements change. Such a pay-as-you-go service model is now widely adopted by the cloud computing service providers, and MapReduce can support it seamlessly to data parallel execution. MapReduce was successfully deployed on thousands of nodes and was able to handle petabytes of data. Efficiency. MapReduce does not need to load the data into a database, which typically incurs high cost. It is, therefore, very efficient for applications that require processing the data only once or only a few times. Fault tolerance. In MapReduce, each job is divided into many small tasks that are assigned to different machines. Failure of a task or machine is compensated by assigning the task to a machine that is able to handle the load. The input of a job is stored in a distributed file system where multiple replicas are kept to ensure high availability. Thus, the failed map task can be repeated correctly by reloading the replica. The failed reduced task can be repeated by repulling the data from the completed map task. So this was a presentation about MapReduce, introducing to the basics of MapReduce. These are some of the references that I've used for this presentation. I hope I hear from you. If there are any questions, you can email me or write in the comments below. Thank you very much.